Let's explore Kepler's laws of planetary motion. There are three laws that make up Kepler's laws of planetary motion: the law of orbits, the law of areas, and the law of periods. They're not officially referred to as such, but it makes them a lot easier to remember. Now, Kepler's first law of planetary motion, the law of orbits, states that the orbital paths of the planets are ellipses, not circles, with the sun at one focus of the ellipse. Generally, all objects that orbit other objects do so in elliptical orbits. An ellipse is a geometric shape that looks like a stretched circle, like an oval. But a circle is just a special type of ellipse. In this animation, we can see that a circle can be stretched into a very long oval, but all the shapes that we're seeing here are considered ellipses. Some are just more stretched than others. We can also notice that the center of the circle splits into 2 points when the circle stretches out, and these points move towards the edges of the oval. These are called the foci of the ellipse. Now, other important parts of an ellipse are the vertices, the semi-major axis, the semi-minor axis, the center of the ellipse, and of course, the 2 foci. It is at one of these 2 foci that the sun is located in the case of a planet orbiting the sun. When the eccentricity of an ellipse increases from 0 to 1, but not quite 1, rather almost 1, we get more and more stretched out oval-shaped ellipses. As the ellipses stretch thinner, their foci separate further apart. And if the foci are both overlapping each other at the center of the ellipse, then that ellipse, with an eccentricity of 0, is a perfect circle. Ultimately, the eccentricity is what determines the exact shape of the ellipse. Now, each of the planets in our solar system, as well as the asteroid belt and other objects that also orbit the sun, have elliptical orbits. Their eccentricities may vary, but the planets, for example, have low eccentricities for the most part. Venus has an almost perfectly circular orbit with an eccentricity of 0.007, whereas Mercury has the most eccentric orbit, at least of the planets, with an eccentricity of 0.206. Kepler's second law of planetary motion is the law of areas. It states that as a planet orbits its parent star, it will speed up on its approach to the star and slow down as it moves further away. This type of motion implies that when a planet is near its parent star, it is moving at a much higher velocity, and it will sweep out a certain amount of area in its orbit. Now, on the opposite end of its orbit, where the planet is furthest from the star, it is moving so slowly that it sweeps out a much thinner area. However, the catch is that these areas are actually equal in size. They just happen to be shaped differently. So if one is hypothetically 1,000 square miles, then so is the other. Thus, Kepler's second law is also referred to as the law of equal areas and equal times. As a planet orbits the sun, not only does it speed up on its approach and slow down as it moves further away from that parent star, it is actually fastest at a point in its orbit called perihelion, where it is physically closest to its parent star at the shortest distance away. At a point on the opposite end of the orbit called aphelion, the planet moves the absolute slowest. One way to remember this is to pair the words peri with perish, since that's what would happen if you get too close to the sun, and to remember the phrase ap and away. I apologize for the cringeworthy pun, but now I guarantee that you'll never forget these words. Kepler's third and final law of planetary motion is the law of periods. It states that a planet's orbital period, the time that it takes to complete one full orbit, measured in years, when squared is equal to its semi-major axis, measured in astronomical units, cubed. Kepler's third law is often represented in equation form as p squared equals a cubed. But it only works when a, the semi-major axis, is measured in units of astronomical units, and p is given in units of years. The distance from the Earth to the Sun is referred to as 1 astronomical unit, abbreviated AU. This is a distance of about 150 million kilometers, which, when written in scientific notation, can be represented as 1.5 times 10 to the power of 11 kilometers. We'll be using the AU as a measure of distance quite a lot in this class, so please make sure that you remember the term and what it's based on.